Okay, this is the title of my talk. In fact, when I received the invitation, I asked you if my talk will fit the theme of your conference, because I notice is like more applied mathematics in it. But anyway, graph considered to be also important subject for engineering and computer science and in general. Okay, so this is the title of my talk, Some Graph on from Rings. And when I decided to give this talk, usually whenever you want to give a talk to a general audience, you have to be careful not to be very technical. So I made sure that I selected some result that I hope you don't need really to know like deep in the subject. Maybe, some of you know at least the basic of a graph and ring theory and so on. Okay, usually in the last maybe three, four talks, I start my talk with this question. Uh, yeah, here is a question. Um, when is the polynomial ring? You think of Rx is like a set of all polynomials with coefficient from a commutative ring R. When this will be a principal ideal ring, meaning every ideal is finite is generated by one element. Uh, Well, when I saw that, I thought, well, this should be done maybe 50 years ago, this kind of question, uh, because seems like, it's a natural thing to ask such question. But what surprised me, the answer, a complete answer to this question, was given in 2018. Which is like recent, if you know, 2000, like 4 years ago. And the answer to the question was given by these two authors, Henry and Lopez. And the answer kind of surprising. I can explain the result almost to anybody. Look at the answer of this question. The polynomial ring over R is a principal ideal ring if and only if R is ring isomorphic to a finite direct product of field. Wow, it cannot be simpler than that. Uh, so we know by this result, for example, we know if your R, your ring, is not a field, then let's see, R is an integral domain that is not a field. Then quickly we know that the polynomial ring over R is not a principal ideal ring. And also we know quickly that the integers modulo n, if you take the polynomial ring over the integers modulo n, then this ring will be a principal ideal ring if and only if uh, n is square free. And I think you know what I mean with square free. Like if I what I'm talking about here is Zn x. So my R is the integers modulo n. Then this ring will be a principal ideal ring if and only if n is square free. Square free, that means when you write n as a product of a prime, then all these primes are to the power 1. You don't have square or cube or whatever. So, for example, we know quickly like z10, the integer, if you take the polynomial ring over the integers modulo 10, then every ideal will be generated by one element. I know quickly if I take the polynomial ring over Z25, this will not be a principal ideal ring. And why? Because the 25 is equal 5 square. Okay? If I take the polynomial ring over let's see, 30, the integers modulo 30, then this ring will be a principal ideal ring. That means every ideal is generated by one element. Why? Because 30 is equal to times 3 times 5. So you get many things for free if you know this result. And it seems I become very addicted to this result. Every time I see it, I get excited because really it's in my views, this is a very beautiful uh, result. So anyway, I will go to my talk. Usually I start my talk with something like I motivate me. Okay. All right. I think there is something maybe missing here or the heading. Okay, I can put this here. All right. Uh, an excellent reference on graph from rings is this recent book by David Anderson, Asir, and myself, and Shilvam. Asir and Shilvam, I think maybe some of you know them. They are from India, and this is a recent book, Graph from Rings in 2021. And I recommend this book if you want to learn more about a graph from rings. Okay, here is the definition. I start with the definition. You have a ring that is commutative, and ZR is the set of zero divisor. Then what we mean with the zero divisor graph of R? We use gamma R for the zero divisor graph of a commutative ring. It's going to be a symbol graph, and whenever you have a graph, you have vertices and you have edges. So the vertices will be the non-zero zero divisor element of the ring. That's ZR star. And two distinct vertices are connected by an edge if and only if when you multiply them, you get zero. Okay? So, I mean, it's very simple definition, but you need to pay attention here that the vertices are not all elements of the ring. The vertices are only the non-zero zero divisor element of the ring. Okay, so now I share with you some nice, what I call from my view, nice result on zero divisor graph. Here is first one. This is by Anderson and Livingston. if you assume that the zero element of the ring is not equal to zero. Okay, so that means your ring cannot be an integral domain. Okay, so you can assume R is not an integral domain. Then the zero divisor graph is finite if and only if R is finite. And this is kind of surprising result, in fact, because what does it say? If the zero divisor is a finite set, then the ring has to be finite. Okay? Of course, the hypothesis that the zero divisor element of the ring is not zero is crucial because somebody might tell me, well, if I take the integers z, then the zero divisor of the ring z just equal 0. But we know z is infinite. But I tell them the hypothesis that the zero element of the ring should not be just 0. So this is very crucial. Otherwise, the theorem will be wrong. So in the street language, how you say this result, if the zero divisor of the ring is not 0, then your ring is finite if and only if the set of the zero divisor is finite. Okay. Okay, here is another one, kind of also an interesting result by Akbari and Muhammadian. Uh, what does it say? If you have a commutative ring that is not an integral domain, what does that mean? That means the set of the zero divisor of the ring is not 0. And assume every vertex of the graph has finite degree, like each vertex is of finite degree, then the ring has to be finite. Wow, that's also kind of interesting because, of course, you have to see the proof to see why. But I find also this is a very nice result uh, on. Well, here is the thing, the question, why do we study a graph on rings? Because, I mean, properties of a graph are also, very nice. But in fact, the main reason for a ring theorist or a group theorist, so maybe you get information about the graph, about the ring. So if I know some properties of the graph, then I know some properties about the ring, like, the one before and this one here. And here is another one. Assume R is a finite commutative ring. If the zero divisor graph is regular, then then the zero divisor graph is either a complete graph or a complete bipartite graph. And what do we mean with regular graph? Regular graph means uh, all vertices have the same degree. That's what we mean with regular graph. Like all vertices are of degree 3, all of them, or all vertices are of degree 2, and so on. So the definition of regular graph, it means that all vertices have the same degree. Okay, and complete graph, all of us know what that meaning between every two vertices there is an edge, line segment. And what do we mean with complete bipartite? That means my vertex set, I can split that into two. Let's call one of them A and the second one B, where every two vertices in A not connected by an edge, and every two vertices in B are not connected by an edge. But every vertex in A is connected to every vertex in B. Okay? So these two result like you get some information in a way on a graph and ring. Uh, in fact, this one here is surprised me because I think in general in a graph this not need to be the case. If your that the regular graph has to be either complete or complete bipartite. But for the zero divisor graph, this is the case. Okay, here is I am giving you the definition of a radius of a graph. Here is the definition in general if you have a connected graph. So your graph is connected. And remember, connected mean like I can go from one vertex to another by a path. And remember what I mean a path. It means by using a sequence of edges, because all of us know the difference between edge and path. Edge means only one line segment that connect two vertices. A path, sequence of edges. Like if I want to go from A to C, maybe I can go from A to B and B to C. So that means I'm using two edges. Okay? All right. So what do we mean with eccentricity of a vertex? EV. The maximum, the distances between V and W, where W is a vertex in V, but of course W is not equal to V. So what you do using street language, if you have a vertex, let's call it V, you measure the distance between V and every other vertex in the graph. And you take the maximum of that. Okay? So this is the eccentricity of a vertex. What do we mean with the radius of the graph? We take the minimum of all the eccentricity. Like, a vertex has four vertices. If you have a graph with four vertices, then you calculate EV1, EV2, EV3, EV4, okay? And then you take the minimum of these four numbers. That will be the radius, okay? Here is a result by Ridman about the radius of the graph. Noetherian, meaning every ideal, is generated by finitely many element. Okay. The radius of the zero divisor graph is zero if and only if R is isomorphic to Z4 or this ring. Radius zero, that means you only have one vertex in a way. Uh, Okay, the radius of the zero divisory graph is 1 if and only if R is isomorphic to Z2 times A, where A is an integral domain. Okay? And continue, if R is finite, then the radius is 1 if and only if uh, either R isomorphic to Z2 time product F, where F is a finite field, or R has exactly one maximal ideal. This is what we mean with R is local, meaning R has exactly one maximal ideal, like the integers the mod 8. This ring has only one maximal ideal, which is generated by 2. Okay? Or like the integers mod 49. This ring has exactly one maximal ideal generated by 7. So the zero divisory graph of finite local rings are always 1. And of course, this case here is clear. Like if you take Z2 product Z5, then also this ring has radius 1. Okay? And this is if and only if. So the radius is 1 if and only if this or this, a complete answer to the question for finite. Okay, the same Ridman. You assume R is commutative Noetherian. That is not an integral domain. Then I know that the radius of the zero divisory graph will never exceed number 2. Oh, that's interesting too. Like if your ring is commutative and Noetherian and you calculate the radius, then it has to be either 0, and we know exactly when it's going to be 0, and we know exactly when it's going to be 1. So for the remaining one, it's going to be at most 2. All right? Okay. Uh, let me mention a chromatic number. What do we mean with a chromatic number of a graph? It means the minimum number of colors that we need in order to color the vertices in a way two vertices that are adjacent will have different color. And what do I mean adjacent? That means they are connected by an edge. Like if I have AB is an edge in a graph, then I want A and B to have different colors. Okay? And the chromatic number is the minimum number of colors we need to color the vertices so that adjacent vertices will have different color. Okay, for the integer by in Indian, Henry, and Manlove, 1, 2, 3. Here is a result on the integers mod n. Assume Km. What Km? Usually for a complete graph with m vertices, we use the this notation, K index by m. Like K4. What does K4 mean? It means like a graph, four vertices, and every two vertices are connected by an edge. Okay? Like what do I mean with K10? K10 mean I have a complete graph, meaning I have a graph with 10 vertices, and every two distinct vertices are connected by an edge, by a line segment. Okay, so if you take the integers modulo n and you assume Km is the largest subgraph, so Km is the largest complete subgraph. Okay, so let me go back. Complete mean every two edges connected by an again two different vertices connected by an edge. So like when I mention K4, I mean complete graph. K10, complete graph with 10 vertices. Okay? All right. So what this result say, if my ring is the integers modulo n and Km, assume that Km is the largest complete subgraph of the zero divisor. So what's missing here after the largest complete, even though Km means complete. Maybe no need to mention it, but for, if you never seen that, maybe you need to know what I mean with Km. Okay, look at the connection. Then the chromatic number is M. If and only if this N here has to be a power of a prime or a product of two distinct prime. Okay? Wow, that's kind of nice in a way. For the integers mod n, a connection between, by the way, this M here in graph theory, they call it a clique number. But I put it in, using, trying to avoid as many terms because I don't need to give definition and I get you confused. So I just, mention exactly what these things mean. Uh, okay, here is another result by Anderson, Fraser, Lovey, Livingston. If your ring A is a product of M integral domains, okay, then K index by M, the same M, is the largest complete subgraph of the zero divisor of A. Okay? And here is another nice result, a connection between this Km and the minimum number ideals of the ring. Assume nil of R equals 0. That means the only nilpotent element in the ring is 0. And M to be the minimum number of the prime ideals of the ring R. Then Km is the largest complete subgraph. This is also a nice result, I call. Okay, so one of the question, when is the zero divisor graph planar? What do we mean with a planar? Or sometimes they call it genus zero. genus, zero, or planar mean the same thing. Mean you can draw the graph on the floor. On the floor, you can draw the graph so that the edges do not cross, they do not intersect. Okay? That's the definition of a planar in a graph theory. Planar mean I can draw it on a piece of paper or on the floor. I can draw the graph so that the edges do not cross or intersect. Okay? This is a very nice, and look at that. This is a complete answer. If your ring is a finite commutative ring, then the zero divisory graph is a planar if and only if your ring is isomorphic to one of the following 44 types of rings. So if you think about this result, it's kind of really, and this is was given by Smith. And I believe Smith, he was a student of David Anderson. Uh, so we have up to isomorphism, we have 44 rings, finite, finite, that where the zero divisory graph of each one of them is planar. And that's kind of, I don't know, if you think about it, it's kind of amazing that we are able to do that, to characterize all the rings where the zero divisory graph is a planar. And this result for finite commutative ring, okay? So in fact, this is hard to type all of them. So I took a picture, as you see, and I insert that in my talk. But this is, I will, let you look at this. There, if you count them, there are 44 different non-isomorphic rings. Okay? Like, each two in the list, they are not isomorphic. Because if they are isomorphic, then I just mention one of them, right? Because look, read the result carefully. Then the zero divisory graph is planar if and only if your ring R is isomorphic to one of these. Okay. Here is also a result by, I'm not sure how you pronounce the name, Yongwei Y Yao. Anyway, here is the name. Uh, Let A be a commutative ring with identity that is not integral domain. So my ring is commutative ring, but not integral domain. Then this ring is infinite, and the zero divisory graph is planar if and only if A is isomorphic to an integral domain times Z2 or times Z3. Okay? Remember in the previous result, we characterize planar for finite commutative rings. Here, this result characterize a planar zero divisory graph in case of your ring is infinite. If your ring is infinite, then the zero divisory graph will be planar if and only if A is isomorphic to a product of an integral domain with Z2 or integral domain with Z3. Nice result. What about uh, genus 1? Remember a graph being planar, another name for a planar, genus 0. So what about genus 1? What do we mean with genus 1? That means I can draw in a way using street language. I can draw my graph on a sphere so that the edges do not cross, do not intersect. That's another meaning for genus 1. And a complete answer is given. Okay. The only restriction here, you're looking at commutative local ring. Remember, local meaning there is only one maximal ideal. And they list all 17 different non-isomorphic rings. So these are the only cases where the genus will be 1, meaning I can draw the graph on a sphere where the edges do not cross. And this result was by, again, the name Chang, Smith, Wang, Wickham. Uh, they gave a complete answer to this case. Okay, here is a result by myself and Anderson. If the set of nilpotent element is a prime ideal and the nil not equal the zero divisor, then the zero divisor graph is a tree if and only if R is infinite, and the zero divisor graph is a star graph. Okay, so if the set of nilpotent element uh, is prime and not equal to the set of the zero divisor element, because all of us know nil of R is a subset of the zero divisor of R, but they are, sometime you have zero divisor element that are not nilpotent. Then the zero divisor graph is a tree. What do I mean a tree? Tree meaning connected graph, but no cycle. Then if this is the case, that means the ring R has to be infinite. And the zero divisor graph is a star graph. Every star graph is a tree, but not every tree is a star graph. What I mean a star graph, mean you have one vertex, call it A, and this A is connected to every other vertex. And all other vertices are not connected by an edge between them. Like if you have three vertices, let's say A, B, C, then A is connected to B, A is connected to C, but B and C are not connected by an edge. That's why we call it a star graph. Okay, I think maybe I'm not sure if do I still have time or I stop here. Hello? Can you hear me? Do I have time or I stop? Okay, I don't think. Okay, thank you. All right. All right. So this is the zero divisory graph. Maybe I will keep you for another 5 or 7 minutes and talk about the annihilator graph. This is was given by Badawi, that's me. If you take a commutative ring, and again Z of R is the set of zero divisor, then the annihilator graph, we use this notation, is the symbol graph with vertex set. You take all zero divisor element of the ring, but you remove zero. And two distinct vertices, x and y, are adjacent if the annihilator of x union the annihilator of y not equal the annihilator of xy. What do we mean with annihilator? It means like annihilator of x means you take all the elements in R that kill x. What do I mean kill? It means when I multiply them with x, I come up with zero. So the annihilator of x, all the elements in R, say y or z or w, where wx equals zero. So all the elements that you in R, and when you multiply them with x, you come up with zero. So you want the annihilator of x union the annihilator of y not equal to the annihilator of xy. Okay, of course, there is another way to say that. I mentioned that the annihilator of x union the annihilator of y is a subset but not equal to the annihilator of xy. Okay, well, I can tell you, why did I think about this definition? I'm trying to generalize the zero divisory graph. So by doing that, the classical zero divisory graph will be a subgraph of the annihilator graph. Okay? So keep in mind that the annihilator graph, we still use the same set of vertices. The difference, how we connect two vertices. The connection, we have to check for the annihilator of the elements. Okay? And keep in mind that the zero divisory graph is a subgraph of the annihilator graph. Assume the set of nilpotent element is zero. Then there is no difference between the annihilator graph and the zero divisory graph if and only if the minimum number of the prime ideals of R is 2. Wow. So that means if you have a ring and the set of nilpotent element is 0 and the minimum prime ideal of the ring, the number of the minimum prime ideal is not 2, then we know that these two graphs are completely different. Because if you look at this result, they are the same if and only if the number of the minimum prime ideal is 2. Okay? Here is another result about the shortest cycle. You assume the set of nilpotent element is 0 and the annihilator graph is different from the zero divisory graph, then I know quickly that the shortest cycle of n, the annihilator graph, is 3. And that means the graph cannot be 3. Because remember, in a tree, you cannot have cycles. All right. This result here kind of, I don't know, interesting. Let's read it carefully. Assume the two graph, the annihilator and the zero divisor graph, are not the same. Okay? If you tell me the length of the shortest cycle of the annihilator graph is 4, then definitely it cannot be 3, if and only if. Okay, well, if it's 4, then definitely it's not the 3. But what is interesting, if I tell you the length of the shortest cycle is not a 3, then it has to be 4, right? Because if and only if. And what's more interesting, the structure of the ring. So if you look at it, all of them if and only if. So if you tell me the annihilator graph not equal the zero divisor graph, and you tell me the girth is 4, then I know exactly the structure of the ring. Then your ring R has to be either this one or this one, not many. Interesting. Okay, I like to finish up. Uh, Also, this is kind of interesting. Let R be a commutative ring and annihilator not equal the zero divisor. If you tell me the zero divisor is a star graph, then I know the annihilator graph has to be K3. What K3? That means the set of non-zero zero divisor has to be 3 element, right? And every two connected by an edge. K3, you think of it as a triangle. That's what K3. But what's interesting, if these two are not equal, if you tell me the zero divisor graph is a star, then I know the ring is finite, right? Because look, what does it mean? The annihilator graph is, that means the set of zero divisor, a non-zero zero divisor element consists of 3. And we have the first result I gave you, that the set of the zero divisor graph is finite if and only if the ring is finite. Anyway, here is my last result. There is a term I defined in maybe 2007, what we mean with two absorbing ideal. It's generalization of a prime. Like if you have a three element in R, and the product of these three element in I, then we should have AB in I, or AC in I, or BC in I. Okay? I introduced this concept, and I introduced the concept of annihilating graph, and I have similar result to the last one, but I consider many cases like the ring reduced, not reduced. But this is a very beautiful result by two Iranian mathematicians, I believe, Birovi and Babai. They give the connection when these two graph are identical. Look at this beautiful result. Then the annihilator graph equal to the zero divisor graph if and only if 0 is two absorbing ideal. That's it. They don't have to, split the ring into reduced, not reduced, like what I did. So they give a very simple result for when these two graph are identical. And I'm done, and I thank you very much. I think I finish on time.